Good morning, everyone. Today I'm going to talk about a project that explores interfacing an 8x8 LED matrix with the Intel 8085 microprocessor using the 8255 programmable peripheral interface. In the standard experiment, we display characters like A, B, and C. But here, I extended the idea to generate custom graphical patterns such as a smiley, heart, and a check mark. The key idea is simple but powerful. The hardware remains the same, but only the data changes, allowing the system to display meaningful visual symbols instead of just text. This demonstrates how even a basic microprocessor like the 8085 can be used for graphical communication using bitmap encoding and multiplexing. Moving on, this slide summarizes both the hardware flow and the working logic of our LED matrix interfacing system using the 8085. So the hardware chain on the left side of the slide, the 8085 CPU, which acts as the brain, it executes our assembly program and generates the data patterns we want to display. The 8255 PPI, we use this as an interface between the CPU and the LED matrix. Port A controls the rows and the port B controls the columns. LED matrix driver. The driver circuitry implemented using a 7407 on the module handles current amplification. This is important because the microprocessor cannot directly drive multiple LEDs safely. Finally, the 8x8 LED matrix, which consists of 64 LEDs arranged in rows and columns. Each LED is addressed by selecting a row and a column simultaneously. How this works is that we first initialize the 8255 using control word 880H, setting all ports as output. Then we do a quick column scan. We activate one column at a time by rotating a low bit across port B. This ensures only one column is active at any instant. For the selected column, we send the corresponding row pattern to port A. An LED glows when its row is high and its column is low. This process is repeated very fast, around 60 times per second. Due to the persistence of vision, the human eye perceives it as a stable image instead of flickering columns. So overall, this system combines hardware interfacing with time multiplexed control to efficiently display complex patterns using limited input-output lines. This slide highlights the key question behind this innovation project. So in the standard experiment, the LED matrix is used to display predefined characters like A, B, and C. These are fixed patterns essentially treated as an alphanumeric display. But why do we have to limit the matrix to letters? Instead of characters, I designed custom bitmap patterns such as a smiley and a heart. These are not predefined. Each pattern is manually created at the bit level and stored in memory. So now the matrix is not just displaying text, it is displaying visual symbols. And the key idea is that the hardware and program structure remain exactly the same, only the data changes. This allows the system to represent universal visual meaning instead of just alphanumeric characters. So this means that the 8085 is not just processing data, it is actually communicating visually. Now, this slide shows the custom bitmap patterns I designed for the LED matrix. Each pattern is stored as 8 bytes in memory, where each byte represents one row of the matrix. Each bit in the byte corresponds to one LED, so this is a direct bit to pixel mapping. The first pattern is a smiley, stored starting at address 2050H. The outer circular boundary is created using values like 3C and 42, while the eyes and facial features are placed using specific bit positions such as A5. This shows how even a simple 8x8 grid can represent expressive shapes. The heart pattern starts at 2058H. It uses values like 66 to form the upper lobes and FF to create a filled region. Then it gradually tapers down using 7E, 3C, and 18 to form the pointed bottom. The checkmark is stored at 2066H. It is designed using a diagonal bit progression, starting from lower bits and moving upward to form the rising stroke. This demonstrates directional patterns using bit control. All of these patterns use the same memory size as standard characters, just 8 bytes each. So again, the key idea is we are not changing the system, only the data stored in memory. Now I'm going to explain how a visual image is converted into hexadecimal data that the 8085 can process. Let's take one row of the smiley pattern as an example. The value A5 in hexadecimal corresponds to binary 101000101. Each bit represents one column of the LED matrix. A 1 means the LED is on and a 0 means it is off, depending on the column being active. So in this case, bits 7, 5, 2 and 0 are high, which means columns 0, 2, 5 and 7 are on for this row. This is how we form shapes, by selectively turning on LEDs across different rows. So the design process is simple and systematic. First we draw the symbol on an 8 by 8 grid. Then each row is converted into an 8-bit binary number. Finally we convert that binary into hexadecimal and store it in memory. Each pattern occupies 8 consecutive memory locations. For example, the smiley is stored from 2050 to 2057, the heart from 2058, and the checkmark from 2060 onwards. So essentially an image is nothing but structured binary data stored in memory. This direct mapping between memory and LEDs is what enables graphical display using a simple microprocessor. Moving on, now we will understand why moving from letters to symbols is actually meaningful, not just visually different. Symbols are universal. For example, a heart represents emotion across all languages, but letters like A, B, or C only have meaning within a specific language context. So symbols enable global intuitive communication. Symbols are recognized faster by the human brain compared to text, so they allow quicker understanding, especially in real-time systems like displays or indicators. From a systems perspective, this is the most important point. The three symbols still use only 24 bytes, exactly the same as displaying A, B, and C. So we achieve more expressive output without any additional memory or hardware cost. Once we treat the display as a bitmap, we can extend this to animation also. By displaying multiple frames in a sequence, we can create effects like blinking or motion. This table now shows how our work extends beyond the standard lab exercise and why it is innovative. In the standard lab, output is limited to alphanumeric characters like A, B, and C. In our project, we move to graphical symbols, enabling richer and more expressive output. Normally, patterns are taken from predefined lookup tables. Here, we designed our own patterns manually on graph paper, which required understanding pixel level representation. Standard experiments do not deal with individual bits. In our case, we explicitly mapped each LED to a specific bit position, which gave full control over the display. Memory usage. So despite this increase in complexity, the memory usage remains exactly the same, 24 bytes. So we achieve higher information density with zero additional memory cost. We use the same column scanning technique as in the standard experiment. This proves that our approach is not hardware dependent, it generalizes on existing systems. Scalability. So the standard approach is limited to ASCII characters. Our method can display any 8 by 8 pattern, making it much more flexible. Standard experiments do not explore animation. We demonstrated that by looping frames, even an 8085 system can produce dynamic visual output. So overall, we did not change the hardware at all. We expanded what it can do through better design. So now we are going to understand how what we just implemented is not a lab concept. It's not just a lab concept. It is the same principle used in many real-world embedded systems, just at a much larger scale. We can see it in stadium scoreboards, where these large displays are essentially massive LED matrix arrays. They display scores, logos, and animations using the same bitmap encoding and scanning techniques, just scaled to thousands of LEDs. You can see it in railway departure boards, where they use dot matrix displays for symbols like on time or delayed. In ATM kiosk interfaces, where uh, these small matrix displays are controlled by embedded processors. You can see it in devices like smartwatches, like LED advertising panels. and also in critical equipment like medical pulse oximeters and monitors, which use matrix-based displays for waveforms and indicators. Reliability in medical equipment is crucial, and the same low-level control of pixels is used. So what we built on an 8 by 8 matrix is essentially a scaled-down model of a real embedded display system. So to conclude, this project demonstrates how a simple microprocessor system can be extended far beyond its conventional use. We successfully interfaced an 8 by 8 LED matrix with the 8085 using the 8255 PPI. All ports were configured as output, and we used column scanning multiplexing to control 64 LEDs efficiently. Instead of displaying the ASCII characters or the predefined ABCs, we designed three custom bitmap patterns from scratch. Importantly, this required the same memory required for those ASCII characters, which is 24 bytes, but gave significantly richer visual output. By refreshing the display at around 60 Hz frequency, we leveraged persistence of vision to produce a stable, flicker-free image. The key takeaway is that the existing hardware was already capable. We simply used it more intelligently. This approach naturally extends to animation, scrolling text, and arbitrary graphics, forming the basis of modern embedded display systems. So this experiment shows that even a basic 8085 system can move from character display to meaningful visual communication. So now I'm going to, this is the proof of execution or the actual experiment I did in the lab with the smiley check mark and the heart face. So let me just play it.
So now for the innovative pattern, I have already entered the code, and my pattern is a smiley, heart, and a checksum. So I'm going to execute it right now. So now for the innovative pattern, I have already entered the code,
So as you
and
can
my
see,
pattern is a smiley, heart, and a checksum.
so the video essentially shows that the patterns you see, smiley, heart, and checkmark, are not stored as characters but as custom bitmap data in memory. And the program continuously scans columns and updates row data at a high refresh rate, creating a stable image. This confirms that the system is not just theoretical, the complete hardware-software integration is working in real time. Also important to note that this is done without any hardware modifications, purely through software level design. Thank you.